Imagine a number you already know. A number you've probably seen in school, maybe even memorized for a test. It starts with 3.14. Simple, ordinary, harmless. But what if I told you that this number never ends? Not just in the usual way, but in a way that no one on Earth can fully predict. The digits keep going forever. No pattern, no repetition, just an endless stream of numbers stretching into infinity. And yet, despite this chaos, it is perfectly exact. Not an approximation, not a guess, exact. How can something be both completely infinite and perfectly precise at the same time? This is not just a mathematical curiosity. This number appears everywhere, in circles, in waves, in the way light moves, even in the structure of the universe itself. Engineers rely on it, physicists depend on it, entire theories collapse without it. And still, after thousands of years, we don't fully understand it. Today, we are going to follow this number far beyond 3.14, into a world where infinity is not just an idea, but something real, measurable, and deeply mysterious. And by the end, you might realize something unsettling. This number is not just part of mathematics, it may be woven into reality itself. It begins with something simple, a circle. Draw a circle on a piece of paper, any size. Now measure the distance around it, then measure the distance across its center. No matter how large or small your circle is, if you divide the distance around it by the distance across, you always get the same number. That number is pi. This fact alone is already extraordinary. Think about it. Circles can be tiny like a coin or enormous like a planet, yet they all obey the same hidden rule. The universe is quietly consistent in a way that feels almost designed. Ancient civilizations noticed this long before modern mathematics existed. The Babylonians, around 1900 BCE, approximated pi as 3.125. The Egyptians, a few centuries later, used a value closer to 3.1605. These were not random guesses. They came from careful measurement, from observing the physical world. Then came Archimedes, who pushed this further. Instead of measuring circles directly, he imagined polygons inside and outside a circle. By increasing the number of sides, he squeezed the true value of pi between two limits. With nothing more than geometry and logic, he showed that pi must lie between 3.1408 and 3.1429. This was a turning point. For the first time, pi was not just measured, it was bounded by pure reasoning. But even then, something strange was already emerging. No matter how far they pushed, no matter how precise the calculations became, pi never settled. It kept extending, more digits, more complexity, no end in sight. At first, this might not seem unusual. After all, many numbers have long decimal expansions. But pi is different. Most numbers you encounter eventually repeat. Take 1 divided by 3, you get 0.3333 forever. There's a clear pattern. Even 1 divided by 7 gives a repeating cycle. 0.142857, repeating endlessly. But pi does not behave like that. Its digits never fall into a repeating pattern, ever. This makes pi what mathematicians call an irrational number. That means it cannot be written as a simple fraction of two integers. No matter how large the numbers you choose, you will never capture pi exactly as a ratio. This was proven in 1761 by Johann Heinrich Lambert. His proof showed that pi is fundamentally beyond fractions. It cannot be simplified. It resists compression. And yet, we can define it exactly. That's the paradox. We know precisely what pi is. It is the ratio of a circle's circumference to its diameter. That definition is exact, perfect, and unchanging. But when we try to express it numerically, it explodes into infinity. It's like having a perfectly clear idea that can never be fully written down. As mathematics advanced, pi began appearing in places where circles were not obvious at all. It emerged in trigonometry, in calculus, in probability theory. It showed up in equations describing waves, heat flow, and even randomness. One of the most surprising appearances comes from a problem that has nothing to do with geometry at all: probability. In the 18th century, a French mathematician named Georges-Louis Leclerc Comte de Buffon posed a strange question. Imagine dropping a needle onto a floor with parallel lines. What is the probability that the needle crosses one of the lines? This seems like a simple experiment, but when you calculate the probability, pi appears in the answer. Not approximately, exactly. This means you can estimate pi by randomly dropping needles and counting how often they cross lines. Geometry, randomness, and probability all connected by the same number. Why? Why should a number defined by circles appear in randomness? This is where pi begins to feel less like a human invention and more like something deeply embedded in reality. And it gets even stranger. In calculus, pi emerges naturally when dealing with waves and oscillations. The sine and cosine functions, used to describe everything from sound to light, are built around pi. These functions repeat every 2 pi units, forming the foundation of periodic motion. This means that whenever something vibrates, oscillates, or moves in cycles, pi is there. Sound waves, light waves, quantum waves, all of them whisper the same number. As physics developed, pi became unavoidable. It appears in equations describing gravity, electromagnetism, and quantum mechanics. It shows up in the equations governing black holes and the expansion of the universe. It is as if pi is not just a property of circles, but a fundamental constant of nature. And yet, despite its importance, its digits remain unpredictable. Computers have calculated trillions of digits of pi. Each time, the digits continue without pattern. No repetition, no structure that we can detect. This leads to a deeper question. Are the digits of pi truly random? At first glance, they seem to be. Statistical tests suggest that each digit from 0 to 9 appears with equal frequency over large samples. But this has never been proven. We don't know if pi is normal, a term mathematicians use to describe numbers whose digits are perfectly uniformly distributed. So even after thousands of years, we are still asking basic questions about this number. We know exactly what it is, but we don't know how its digits behave. That tension between certainty and mystery is what makes pi so fascinating. Now let's go deeper. If pi never ends and never repeats, then it contains an infinite sequence of digits. Within that infinite sequence, something remarkable becomes possible. Any finite sequence of numbers must appear somewhere in pi. Your birthday written as digits, a phone number, a book encoded in numbers, even the entire text of human history if converted into numerical form. All of it could, in theory, be hidden somewhere within pi. This idea depends on whether pi is normal, which remains unproven. But if it is true, then pi is not just infinite, it is unimaginably rich. It becomes a kind of infinite library containing every possible finite pattern. This concept blurs the line between mathematics and philosophy. If every possible sequence exists within pi, then every story, every idea, every piece of information is encoded somewhere in its digits. Not in any meaningful order, but present nonetheless. It's a strange thought. A single number defined by a simple ratio, potentially containing everything. And yet, we have no way of finding most of it. Even with modern computers, we can only calculate a tiny fraction of pi's digits. The rest stretches beyond our reach, forever hidden. This raises another question. Is pi discovered or invented? Did humans create pi as a mathematical concept, or did we uncover something that already existed in the structure of reality? Most mathematicians would say pi is discovered. Circles exist independently of us. The ratio between circumference and diameter is not something we chose, it is something we found. But then, why does this ratio lead to such complexity? Why does something so simple produce something so infinite? This is where mathematics begins to feel almost alive, full of patterns, surprises, and unanswered questions, and pi sits at the center of it all. As we move beyond the basics, one of the most striking appearances of pi is in the realm of complex numbers and exponential functions. Euler's identity, often called the most beautiful formula in mathematics, connects pi, the imaginary unit I, and the natural exponential constant e in a single elegant equation. E to the I pi plus 1 equals 0. This equation is astonishing because it unites 5 of the most fundamental constants in mathematics, 0, 1, e, I, and pi, into a single relationship with no approximations. It seems almost magical. A constant that starts from geometry and circles now governs the behavior of complex exponentials. The same pi that measures the ratio of a circle's circumference to its diameter also emerges naturally when dealing with rotations in the complex plane. Why does this happen? The answer comes from the way exponential functions and trigonometric functions relate to each other. Using the Taylor series expansions for e to the x, sine of x, and cos of x, mathematicians discovered that a rotation through the complex plane can be expressed as a sum of infinitely many terms, and pi naturally appears as the scaling factor that completes a full rotation. This is not just an abstract curiosity. It underpins electrical engineering, signal processing, and even quantum mechanics. Without pi, none of these systems would function mathematically. Speaking of quantum mechanics, pi also appears in the probability amplitudes that govern the microscopic world. In Schrödinger's equation, the wave function psi describes the probability distribution of particles. When solving this equation for systems such as a particle in a box or the hydrogen atom, pi repeatedly emerges in the normalization constants and in the expressions for energy levels. For example, the energy levels of a hydrogen atom involve pi in the denominator of the formula. E to the n equals minus me to the fourth over 8 epsilon 0 squared h squared n squared. Here, hidden in the derivation of constants, pi appears in the relation between Planck's constant, the permittivity of free space, and the geometry of the system. Essentially, the seemingly abstract concept of a circle governs the structure of atoms themselves. Even more astonishing is pi's appearance in probability and statistics at a fundamental level. The Gaussian distribution, or normal distribution, the bell curve ubiquitous across natural phenomena, contains pi in its formula. F of x equals 1 over 2 pi sigma squared times e to the minus x minus mu squared over 2 sigma squared. This means that every time we model random processes from measurement errors to population behavior, pi is quietly embedded in the mathematics. It appears not because of circles, but because the distribution arises from the fundamental properties of space and symmetry in the real numbers. The infinite nature of pi is woven into the very shape of uncertainty itself. To understand why pi is so omnipresent, mathematicians have explored its infinite series in products. For instance, the famous Leibniz series expresses pi as this: pi over 4 equals 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and so on. At first glance, it seems almost impossibly slow to converge, yet this simple alternating series perfectly captures the infinite nature of pi, demonstrating its balance and inherent harmony. Later, Ramanujan discovered far more rapidly converging series, allowing pi to be calculated to millions and then trillions of digits. These series are not just numerical tricks, they reveal deep symmetries in number theory, modular forms, and complex analysis. Ramanujan's work also connected pi to modular functions, which are key in modern cryptography and even string theory. In some sense, the same number that defines the geometry of a circle also plays a role in the most abstract branches of pure mathematics centuries after its discovery. In physics, pi even appears in cosmology. The surface area of a sphere is 4 pi r squared, and the volume is 4/3 pi r cubed. This is fundamental when calculating the size of stars, planets, and even estimating the observable universe. When scientists measure the cosmic microwave background or calculate the volume of voids and clusters in space, pi is silently governing these large-scale structures. Every calculation of energy density, entropy, or angular momentum involves pi, making it both a microscopic and cosmic constant. But let's push further into abstraction. Computational mathematics has revealed that pi is also essential in random number generation, Fourier transforms, and even chaos theory.
The fast Fourier transform, for instance, decomposes signals into sine and cosine waves, each of which depends on pi to define the frequency. Without pi, our ability to compress audio, process images, or analyze vibrations would collapse. Chaos theory, such as in the study of the logistic map, also often involves pi indirectly through bifurcation diagrams and trigonometric transformations.
This duality, pi as both infinitely precise and unpredictably complex, is mirrored in how mathematicians attempt to compute it. Modern algorithms like the Chudnovsky formula can generate billions of digits extremely quickly. Yet even after trillions of digits, no pattern emerges, confirming the infinite, almost mysterious complexity of pi. Here you begin to see a recurring theme. Pi bridges simplicity and infinity. On one hand, it is a single exact definition, the ratio of circumference to diameter. On the other, it manifests across mathematics, physics, probability, and even the very structure of reality in ways that are unpredictable and infinitely detailed. This raises profound questions about the nature of numbers, infinity, and reality itself. Is pi a reflection of a hidden order in the universe, or is it simply a property of the abstract world of mathematics? Its digits man-code randomness, yet its applications enforce precision and symmetry. It is a paradox in numeric form, perfectly defined, infinitely complex, universally present. We haven't even reached its deepest connections. Pi also appears in the study of topology, complex dynamics, and analytic number theory. Consider the Riemann zeta function, zeta of S, which is critical in understanding the distribution of prime numbers. The zeta function at even positive integers is directly related to pi. Zeta of 2 equals pi squared over 6, zeta of 4 equals pi to the 4th over 90, and so on. This is remarkable. A number arising from circles appears in the structure of prime numbers, which underpins all of arithmetic. From geometry to number theory to physics, pi seems to be a hidden thread connecting disparate realms of knowledge. At this point, we begin to see that pi is not just a number. It is a conceptual bridge across mathematics, physics, and even philosophy. Infinity, randomness, symmetry, oscillation, and cosmic structure all intersect through pi. We now step into the realm where pi intersects quantum physics, complex analysis, and computational limits. In quantum mechanics, pi is not merely a constant in wave functions. It fundamentally determines the scale and structure of phenomena at the subatomic level. For example, in the path integral formulation developed by Richard Feynman, the probability amplitude for a particle to move from one point to another is calculated by summing over all possible paths, each weighted by an exponential of the action divided by h bar, the reduced Planck constant. Here, pi emerges naturally in the normalization constants of the Gaussian integrals used in the functional summation. These integrals are crucial. They guarantee that probabilities sum to 1, ensuring the internal consistency of the theory. Without pi, the very framework of quantum mechanics would collapse. Similarly, in quantum field theory, pi appears in loop calculations, vacuum expectation values, and the formulation of propagators. For instance, the propagator of a free scalar field in four-dimensional spacetime involves factors of 1 over 2 pi to the 4th in momentum space integrals. These factors are not arbitrary. They arise from Fourier transforms over infinite space, ensuring that the theory preserves Lorentz invariance. Essentially, pi ensures that the universe behaves consistently across space and time at the quantum level. Moving into statistical mechanics, pi surfaces in the normalization of multi-dimensional Gaussian distributions, which describe thermal fluctuations of particles. Consider a system of n particles in a potential well. The partition function, which encodes all thermodynamic properties, involves integrals over positions and momenta. These integrals often take the form of Gaussian multivariate distributions, each contributing a factor of square root of 2 pi per degree of freedom. The remarkable consequence is that pi directly affects entropy calculations, heat capacities, and the distribution of energies in real physical systems.
Even though pi is abstract, it governs tangible properties like temperature and pressure. From a computational perspective, the study of pi has revealed profound insights into the limits of calculation. Modern algorithms such as the Chudnovsky algorithm, BBP, Bailey-Borwin-Plouffe formula, and Ramanujan type series enable the computation of trillions of digits of pi. The BBP formula is particularly fascinating because it allows the calculation of arbitrary hexadecimal digits of pi without computing all preceding digits, a breakthrough that was once thought impossible. This discovery not only advances number theory, but also tests the limits of what is computationally feasible. It demonstrates that pi is intertwined with algorithmic complexity, randomness, and the theoretical foundations of computer science. Furthermore, pi connects with information theory. The digits of pi appear statistically uniform, passing most randomness tests, suggesting that pi could serve as a pseudo-random number generator in cryptography and stochastic simulations. Yet, despite billions of calculated digits, no pattern has been discerned, highlighting the tension between determinism, pi is exact, and apparent randomness, its digits behave unpredictably. This duality is deeply analogous to phenomena in nature, such as quantum fluctuations, where deterministic laws produce outcomes that appear random. In pure mathematics, pi plays a central role in the study of modular forms and complex analysis. For example, Ramanujan type series for 1 over pi are deeply connected to modular functions and elliptic integrals, objects that form the backbone of modern number theory and string theory. The transcendental nature of pi, proven by Lindemann in 1882, ensures that pi cannot satisfy any algebraic equation with rational coefficients. This fact has profound consequences. It renders classical problems like squaring the circle mathematically impossible, yet simultaneously opens a gateway into advanced fields of transcendental number theory and Diophantine approximations. In topology and geometry, pi arises naturally in the study of curvature and manifolds. Consider the Gauss-Bonnet theorem, which relates the integral of curvature over a closed surface to the Euler characteristic, an integer topological invariant. The integral often includes pi explicitly, demonstrating that pi governs not only measurements, but the intrinsic shape and connectivity of space itself. This connection between continuous geometry and discrete topological invariance exemplifies how pi bridges seemingly distinct mathematical realms.
Extending even further, in fractal geometry and chaos theory, pi appears in the analysis of oscillatory and self-similar systems. Fourier series, which decompose functions into sums of sines and cosines, rely fundamentally on pi to define the period and phase of each component. These series allow mathematicians and physicists to analyze complex, seemingly chaotic systems, turbulent fluids, weather patterns, or population dynamics by breaking them into simpler periodic structures. Without pi, the decomposition of complexity into analyzable components would be impossible, highlighting its central role in understanding emergent behavior in nature. In cosmology, pi is indispensable in calculations involving the geometry of spacetime. General relativity describes gravity as the curvature of spacetime, and many formulas involve integrating over spherical volumes, surface areas, or hypersurfaces, each producing factors of pi. The Schwarzschild radius of a black hole, the area of event horizons, and even entropy calculations in black hole thermodynamics all feature pi. In fact, the Bekenstein-Hawking formula for black hole entropy is proportional to the horizon area divided by 4 times the Planck area, and the horizon area contains pi squared. Once again, pi links the abstract world of mathematics directly to the extreme conditions of the physical universe. Even more intriguing is pi's role in the deep structure of prime numbers. The Riemann zeta function, zeta of s, is central to understanding prime distribution, and as noted, zeta of 2 equals pi squared sixths, zeta of 4 equals pi to the 4th 90ths, and so on. This shows that pi is not only geometric and physical, but also intimately connected to the arithmetic of the integers themselves. Through this connection, pi forms a hidden bridge between continuous analysis and discrete number theory, linking chaos, randomness, and fundamental structure in mathematics. At this stage, it becomes clear that pi is far more than a simple ratio. It is an exact constant, an infinite sequence, a statistical phenomenon, a computational challenge, and a cosmic regulator. It governs atoms, stars, waves, fluctuations, and primes. It is deterministic yet unpredictable, simple yet infinitely complex. Mathematicians, physicists, and computer scientists continue to explore pi not merely for calculation, but as a gateway into understanding the limits of knowledge itself, the boundaries of infinity, the structure of randomness, and the deep order underlying reality. One of the most profound places pi appears is in the structure of Fourier analysis, which underlies almost all modern science and engineering. Any signal, sound, light, temperature variation, even brain activity, can be decomposed into a sum of sine and cosine waves. These waves are periodic, and their periodicity is defined in terms of pi. What makes this remarkable is that any complex behavior can be broken into simple oscillations governed by pi. A chaotic signal is not truly chaotic. It is a superposition of infinitely many ordered waves. This means pi is not just describing circles anymore. It is describing how complexity itself can be understood and reconstructed. This becomes critical in quantum mechanics, where wave functions are expanded in Fourier series. The position and momentum of a particle are related through Fourier transforms, and the uncertainty principle emerges directly from this relationship. In a very real sense, pi sits at the heart of why we cannot simultaneously know position and momentum with perfect precision. Now consider non-Euclidean geometry, where space itself is curved. In flat geometry, the circumference to diameter is always pi, but in curved spaces, this ratio changes. On a sphere, for example, the circumference of a circle is smaller than what Euclidean geometry predicts. In hyperbolic space, it is larger. This means something subtle but profound. Pi is constant, but the geometry of space determines how it manifests physically. In general relativity, massive objects curve spacetime. This curvature affects distances and angles, meaning that the effective geometry of the universe can deviate from flat space. Yet pi still appears in the equations governing these geometries. It becomes a kind of reference constant, a baseline against which curvature is measured. So pi is not just embedded in space, it helps define what space even means. Let's move into analytic number theory, where pi appears in places that seem completely unrelated to geometry. The distribution of prime numbers, those indivisible building blocks of arithmetic, follows patterns that are deeply connected to the Riemann function. And, as seen earlier, pi appears in exact values of this function. But it goes deeper. The zeros of the zeta function, points where it equals 0, are believed to encode the exact distribution of primes. This is the famous unsolved problem known as the Riemann hypothesis. If proven, it would unlock a precise understanding of how primes are spaced. And pi is woven into the equations that define this function. So a number that begins with circles may ultimately govern the hidden structure of prime numbers, the foundation of arithmetic and modern cryptography. Now step into higher dimensions. In 2 dimensions, the circumference of a circle involves pi. In 3 dimensions, the surface area and volume of a sphere involve pi. But in higher dimensions, something even more surprising happens. The volume of an n-dimensional sphere depends on pi raised to fractional powers. As the number of dimensions increases, the behavior of these volumes becomes counterintuitive. For example, the volume of a high-dimensional sphere eventually shrinks towards 0 even as the space it exists in grows. Pi continues to appear in these formulas, acting as a constant that governs geometry even in spaces we cannot visualize. This is not just abstract mathematics. In theories like string theory, the universe may have more than 3 spatial dimensions. Calculations in these frameworks rely heavily on multidimensional integrals where pi is unavoidable. In quantum field theory, pi appears in renormalization, the process used to remove infinities from physical predictions. When calculating particle interactions, integrals often diverge, producing infinite results.
physicists developed renormalization techniques to extract finite, meaningful values. These calculations frequently involve factors of pi arising from integration over momentum space. The presence of pi ensures that the corrected values match experimental observations. This is extraordinary. Even when equations break down into infinities, pi remains part of the structure that restores physical meaning. Another deep connection emerges in random matrix theory, which studies large matrices with random entries. Surprisingly, the statistical distribution of eigenvalues in these matrices matches the distribution of zeros of the Riemann function. And again, pi appears in the formulas describing these distributions. This suggests a hidden unity between randomness, prime numbers, and spectral theory, fields that seem unrelated at first glance. Now consider information and computation at a fundamental level. There is a concept known as algorithmic randomness. A sequence is considered random if there is no shorter algorithm that can produce it. The digits of pi appear to behave randomly, yet pi itself can be generated by relatively short algorithms. This creates a paradox. Pi is highly compressible in definition, but incompressible in its expansion. This dual nature mirrors deep questions in physics and computation. The universe itself may operate under simple laws, yet produce outcomes that are effectively unpredictable. Pi becomes a model for how simple rules can generate infinite complexity.
In thermodynamics and entropy, pi also plays a role in phase space calculations. The number of possible states of a system is determined by integrals over position and momentum, often resulting in factors involving pi. Entropy, which measures disorder, is therefore indirectly tied to pi. This connects the constant not just to structure and order, but also to randomness and chaos. Finally, consider a philosophical perspective grounded in mathematical realism. If pi exists independently of human thought, then it was there before any mind discovered it. The ratio of a circle's circumference to its diameter would still be pi in any possible universe with consistent geometry. But the infinite digits, the endless, patternless expansion raise a deeper question. Does this infinite information truly exist in a physical sense, or is it only a potential that unfolds as we compute it? Some physicists argue that the universe itself may not contain infinite information. If so, then most of pi's digits are not physically real. They are mathematically defined but never instantiated in reality. This creates a tension between mathematics and physics. Mathematics allows infinity. Physics may impose limits. And pi sits precisely at that boundary. At this point, pi has taken us through geometry and circles, waves and oscillations, quantum mechanics and probability, prime numbers and deep number theory, higher dimensions and cosmology, computation and randomness, and the limits of physical reality. And yet, despite all of this, its digits continue endlessly, silently, without pattern. A number that begins with something as simple as a circle has become a gateway into the deepest structures of knowledge. Consider this. Every time we write down pi, we assume it has infinitely many digits. But the physical universe is finite, at least in terms of the information it can store. Modern physics suggests there is a limit to how much information can exist in a given region of space. This idea comes from black hole thermodynamics and is formalized in what's known as the Bekenstein bound. It states that the maximum amount of information contained in a region is proportional not to its volume, but to its surface area. And that surface area involves pi. A sphere's area is 4 pi r squared, so the maximum information content of a region of space is directly tied to pi. This means pi is not just describing geometry, it is setting limits on information itself. Now think carefully. If the universe has a finite information capacity, then it cannot physically store all digits of pi, not even close. Even if you used every particle in the observable universe as a bit of storage, you would still only encode a finite portion. So here's the unsettling implication. Most of pi's digits do not and cannot exist physically. They are mathematically defined, but never realized. This creates a deep divide between mathematical infinity and physical reality.
Now move into black hole physics, where pi appears in one of the most important equations ever discovered. The entropy of a black hole is given by the Bekenstein-Hawking formula. It shows that entropy is proportional to the area of the event horizon. Since the horizon is spherical, pi is embedded directly into the equation. What this tells us is profound. The amount of information hidden inside a black hole, everything it has ever absorbed, is encoded on its surface, not its interior, and pi is part of that encoding. So pi is not just involved in describing space, but in describing what can be known about space. Now consider quantum gravity, an area still not fully understood. In attempts to unify quantum mechanics with general relativity, physicists often encounter pi in path integrals, partition functions, and geometric quantization. In loop quantum gravity, for instance, the quantization of area involves factors that ultimately connect back to pi through geometric relations. In string theory, pi appears in the formulation of string amplitudes and compactified dimensions. When extra dimensions are curled into tiny shapes, often modeled using complex manifolds, their volumes and properties involve pi in higher dimensional integrals. This suggests something remarkable. Even in theories that attempt to describe the most fundamental structure of reality, pi is unavoidable. Now let's go into measurement. In practice, we never measure pi directly. Instead, we measure physical quantities, circumference, diameter, wavelength, and infer pi from them. But every measurement has uncertainty. No matter how precise our instruments become, we can never extract more than a finite number of digits of pi from the physical world. There is always noise, always limitation. So while pi is exact in mathematics, any physical realization of pi is approximate. This creates a layered reality. Pi in mathematics is exact, infinite. Physical pi is measured, finite, and approximate. And yet, physics relies on the exact version to make predictions. Now consider something even deeper. Is the universe continuous or discrete? If space and time are continuous, then pi fits naturally. It describes smooth curves and perfect geometry. But if the universe is discrete at the smallest scale, as some quantum gravity theories suggest, then perfect circles may not exist. Space might be made of tiny pixels, and curves are only approximations. In such a universe, pi would not arise from perfect geometry, but as a limit of discrete approximations. This raises a radical possibility. Pi might not be fundamental. It might emerge from deeper, discrete rules. Now move into experimental physics. Pi appears in wave behavior, light, sound, quantum fields. When we measure frequencies, wavelengths, and oscillations, pi is embedded in the equations we use. For example, the relationship between wavelength and frequency involves factors of 2 pi when expressed in angular frequency. This is not arbitrary, it reflects the periodic nature of waves. Experiments in optics, acoustics, and quantum systems all confirm predictions that rely on pi. This is one of the strongest pieces of evidence that pi is not just abstract, it is physically real in its consequences. Now let's approach cosmology again, but more critically. If the universe is curved, then large-scale measurements of geometry could, in principle, detect deviations from Euclidean pi. Astronomers have attempted this by measuring the angles of large triangles formed by distant galaxies. So far, observations suggest that the universe is very close to flat, meaning pi behaves as expected at cosmic scales. But if future measurements detect curvature, then the effective pi at large scales could differ slightly from the mathematical constant. This would not change pi itself, but it would change how geometry manifests in reality. Now consider the ultimate computational question. Can pi ever be fully known? The answer is no, not in practice, and possibly not even in principle. Even though pi is computable, meaning there exists an algorithm to generate its digits, computing all digits would require infinite time and resources. So pi represents something unique, a number that is perfectly defined but never fully accessible. This leads to a final, deeper layer of interpretation. Pi embodies a fundamental tension. Finite beings, like us, trying to understand infinite structures. We can define pi in a single sentence, but we can never fully write it down. We can use it to build technology, predict physical phenomena, and explore the universe, but we can never exhaust it.
At this level, pi stops being just a number. It becomes a boundary between simplicity and complexity, determinism and randomness, mathematics and physics, finite and infinite. There is a concept in physics known as path integrals, introduced by Richard Feynman. Instead of a particle taking one path from point A to point B, quantum mechanics considers every possible path simultaneously. Each path contributes to the final outcome, weighted by a phase factor. That phase factor contains pi. More precisely, it involves complex exponentials where oscillations are measured in cycles of 2 pi. The interference between these paths, constructive and destructive, is what produces the observable behavior of particles. So what we perceive as a single definite reality is actually the result of infinite oscillations structured by pi. Without pi, these oscillations would not align correctly. Interference patterns would break. The quantum world would not produce stable outcomes. Now consider quantum electrodynamics, QED, one of the most precise theories ever created. Predictions from QED match experimental results to more than 10 decimal places. In these calculations, pi appears repeatedly in integrals over momentum space, loop corrections, and normalization constants. The famous calculation of the electron's magnetic moment, one of the most accurate predictions in science, depends on terms involving pi. This is not coincidence. Pi is part of the mathematical structure that allows theory and experiment to agree with extraordinary precision. Now we go deeper into renormalization and infinities. When physicists calculate interactions at very small scales, equations often produce infinities. These are not physical, they are artifacts of the mathematical framework. To fix this, physicists developed renormalization, a method of absorbing infinities into measurable quantities. During this process, pi appears as part of the correction terms that regularize the equations. This means pi is embedded in the very process of turning infinite meaningless results into finite physical predictions. So pi is not just part of equations, it is part of how physics rescues itself from breakdown. Now consider spectral geometry, a field that studies how shapes relate to vibrations. There's a famous question: can you hear the shape of a drum? The frequencies at which a drum vibrates depend on its shape, and these frequencies are determined using equations involving pi. The eigenvalues of the Laplacian operator, central to this problem, contain pi in their formulation. This connects geometry, sound, and analysis. It tells us that pi governs not just static shapes, but how shapes respond dynamically. Now we approach something even more abstract: holography. Modern theoretical physics suggests that the universe may be described by the holographic principle, where all information in a volume of space can be encoded on its boundary. That boundary, often modeled as a surface, involves geometry, and therefore pi. In the context of the ADS-CFT correspondence, calculations of entropy, correlation functions, and field interactions frequently involve pi through integrals over curved spaces. This suggests that pi is part of the translation layer between different descriptions of reality. Now let's move into extreme computation and limits of knowledge. There is a concept known as computational irreducibility, introduced by Stephen Wolfram. It states that some systems cannot be simplified. You must simulate every step to know the outcome. Pi may exhibit a similar property. Even though we have formulas to compute it, there is no known shortcut to predict arbitrary digits without computation. Each new digit requires work. This suggests that pi is not just infinite, it may be irreducibly complex. Now consider randomness and determinism more deeply. The digits of pi pass statistical tests for randomness, but pi is not random, it is generated by deterministic rules. This creates a profound paradox, a deterministic system producing outputs indistinguishable from randomness. This is mirrored in physics. Quantum mechanics is governed by precise equations, yet produces probabilistic outcomes. Pi becomes a mathematical analog of this phenomenon. Now we approach a speculative but serious idea in the philosophy of physics: mathematical realism. Some physicists, like Max Tegmark, have proposed that the universe is not just described by mathematics, it is mathematics. In this view, constants like pi are not properties of the universe, they are the universe.
If this is true, then pi is not embedded in reality. Reality is embedded in pi-like structures. Now consider information encoding inside pi. If pi is normal, still unproven, then every finite sequence of digits appears somewhere within it. This means any piece of information, text, images, even entire simulations, could in principle be encoded within pi. Not intentionally, not meaningfully, but mathematically present. This transforms pi into something like an infinite information reservoir. But here is the critical limitation. Finding a specific sequence within pi is computationally infeasible. The information exists, but it is effectively inaccessible. So pi contains everything and yet reveals almost nothing.
Now we move into measurement limits in physical constants. In physics, constants like the speed of light, Planck's constant, and gravitational constant define measurable reality. Pi is different. It is not measured, it is derived. Yet it appears in equations involving all these constants. This makes pi a kind of structural constant, not tied to a specific force or interaction, but to the geometry underlying all of them. Now consider the ultimate limit. If the universe has finite age and finite computational capacity, then there is a maximum number of operations that could ever be performed. This implies a maximum number of digits of pi that could ever be computed, even in principle. Beyond that point, pi exists only as an abstraction. This creates a boundary: known pi, finite, computed; unknown pi, infinite, uncomputed. And that boundary may never be crossed. At this level, pi becomes something profoundly unsettling. It is fully defined, yet never fully known. It is deterministic, yet indistinguishable from randomness. It is infinite, yet physically inaccessible. It is simple in origin, yet infinitely complex in expression. And perhaps the deepest insight is this: pi does not just describe circles. It does not just appear in equations. It reveals something about the nature of knowledge itself. That there exist truths which are perfectly precise, but forever beyond complete understanding. There's a growing line of thought in theoretical physics and mathematics that reality may behave like a form of computation, not in the simplistic sense of a computer simulation, but in the deeper sense that the universe evolves according to rules, rules that transform information over time. If this is true, then constants like pi are not just values inside equations, they are part of the rules themselves. In such a framework, pi functions like a structural constant that governs how transformations behave. Rotations, oscillations, interference patterns, all of these rely on relationships encoded through pi. It becomes less like a number you use and more like a constraint you cannot escape. Now consider how perception works. The human brain processes signals, light, sound, motion, by decomposing them into frequencies. This decomposition is mathematically equivalent to Fourier analysis, which depends fundamentally on pi. That means every sound you hear, every image you see, every pattern you recognize is processed through structures defined by pi. You do not directly see pi, but your brain uses it constantly to construct reality. So in a very real sense, pi is not just out there in the universe, it is part of how you experience the universe. Now move into a deeper speculative boundary. Can structure emerge from pure mathematics alone? If pi's digits are truly patternless, but contain all possible finite sequences, then any structured pattern, language, images, even intelligence, exists somewhere within it in encoded form. Not arranged meaningfully, not accessible, but present. This leads to a radical perspective. Complexity does not always require design. It can emerge from pure combinatorial inevitability. In pi, every possible finite structure is not created, it is contained. But here lies the limitation. Existence is not the same as accessibility. The structure is there, but without a mechanism to extract it, it remains indistinguishable from noise. Now consider consciousness in this framework. Consciousness, as far as we understand, arises from patterns of information processing in the brain. These patterns are physical, but they can also be described mathematically. If mathematical structures can in principle encode any finite pattern, then there is a conceptual possibility, however remote, that structures equivalent to conscious processes could exist abstractly within mathematical objects like pi. Not alive, not aware, but structurally equivalent. This idea does not claim that pi thinks or contains minds. It highlights something more subtle, that the boundary between structure and meaning is not inherent. It depends on interpretation and context.
Now, step back and look at the full picture. Pi began as a simple ratio, a circle, a measurement, a geometric fact. But as we followed it deeper, it revealed itself in oscillations and waves, probability and randomness, quantum mechanics and field theory, prime numbers and deep arithmetic, higher dimensions and cosmology, computation and information theory, and even the limits of what can be known. At every level, pi did not just appear, it connected. It linked ideas that seemed unrelated. It bridged disciplines that rarely intersect. It acted as a kind of hidden constant, tying together the structure of knowledge itself. Now we arrive at the final tension. Pi is infinite, but the universe may not be. Pi is exact, but measurements are not. Pi is fully defined, but never fully accessible. So what does pi ultimately represent? It represents a boundary, not just between numbers, but between what can be known and what cannot. It shows that even in a universe governed by precise laws, there exist truths that are complete in definition, yet incomplete in experience. You can understand pi, you can use pi, you can calculate more and more of it, but you can never finish it. And that may be the most important insight of all, because it suggests that reality itself may share this property: structured, knowable, predictable in parts, but never fully exhaustible. Pi never ends, not just in its digits, but in what it reveals. It is a constant that begins with a circle and leads all the way to the edge of understanding.